So in this public lecture, I would like to advocate one idea, that sometimes wrong theories can be very beautiful and somehow useful. I want to describe for you a theory that was born 150 years ago, which was completely wrong, but which turned out to be a good idea. Another idea I would like to focus on today is that I would like to explain that mathematics is unity. And I will give you examples of branches of mathematics that look very different and that finally merge and produce some beautiful mathematics. So if you allow me, and since it's a public lecture, I would like to share with you my own feeling now. You know, giving such a talk in front of such an audience is not easy, and really the way I feel now is that I feel lonely. I have no idea of who is in front of me. I was expecting this, and I find that. So I'm not joking. It's a serious question. We have to discuss, and mathematicians are organizing more and more public lectures. It's a good thing, but it would be very important for us to understand what is a public, to whom I am speaking, which is, as you can understand, a very difficult challenge for me to speak for all of you now. So since you guessed or understood quickly that I'm French, I want to begin by René Descartes. René Descartes is fantastic, and one of the important things that he did was that he decided that the world should be mechanical. It should be some kind of big machine that would explain everything, like gears rotating one around the other. Or even better, he was imagining like a fluid, like an ether, filling the space and transporting all information, transporting forces, light, matter. For Descartes, matter and space were just the same thing. Matter, space, energy, force, the same thing. You see the dates? In 1644, he constructed the first vortex theory, explaining the world. So in the middle of the world, there was a big vortex created by the sun, and some secondary vortices created by other planets, and some microscopic vortices, and everything was rotating and producing this big machine, producing movement. Of course, this theory was completely wrong, but during a long time, it was accepted by all scientists, in particular by the French scientists, against the British, of course. Because the guy who was against that was Newton. Newton had a very different view on space. When you think of the space, what could it mean to say the space is empty? There is nothing between, say, the Earth and the sun. What does that mean to be empty? As I told you, Descartes would not accept empty space. In the case of Newton, he did not accept it either. But his conception of space was much more conceptual. In the case of Newton, Newton was calling empty space sensorium Dei, the sense of God. So for him, the empty space was indeed empty, but was the substratum that was the connection between God and the human beings. So he wrote something like, in his famous book on philosophy, I mean natural philosophy, he wrote, speaking of the empty space, he said, "It is the dominion of a spiritual being which constitutes God. In him are all things contained and moved." So I want to insist on this point of view relating space with God, because you will see that this idea of connecting science and religion has been something very important for centuries, and even today. So the main characters that I want to introduce you today, the first one is Peter Tate. Well, he was not French, but almost. He was from Scotland. I like him very much. He was a poet, he was a musician, he was a golf champion, he was a physicist, he was a mathematician, he was, I learned this concept recently, a senior wrangler. Everybody knows what senior wrangler is? No? Amy, you don't know? So I was told that in Cambridge, not in Oxford, in Cambridge, the top student in mathematics is called a senior wrangler. It's a great honor. And Tate was senior wrangler. And the second hero of my talk today is William Thomson, Lord Kelvin. He was convinced he would be senior wrangler. And before the announcement of the results, he sent his servant asking him, "Go and tell me who is the second." And the servant came back and said, "You, sir." This is a true story, I read it recently. Kelvin is really also a great mathematician, great physicist, great engineer. You know, this is good old times where you could be a mathematician and engineer and physicist and a businessman and everything. And in the case of Kelvin, for example, Kelvin was the first to try to embed a transatlantic cable on the bottom of the Atlantic Ocean. And his first attempt in 1865 was a disaster. They began putting on the bottom of the ocean this cable, and after 1,200 miles, they lost the cable. You can imagine the amount of money that they lost. I mean, that has been a real disaster. They had to do it again and again, and finally, they established the first transatlantic connection between the Queen Victoria and who was the President of America in 1869? Amy? I don't know. Anyway, so he was really engineer. And he wanted also to think everything in a concrete way. So we have to discuss vortices today. Vortices deal with fluids, fluids which are moving and which are spinning and rotating. So I want to spend some time, because, you know, since I'm a mathematician, I like to define the words that I use. So I want to define the word vortex. And I will not use too many formulas, but we need some understanding of what is a vortex. This is a vortex. Imagine you are in a small rowboat in this vortex. I hope not. And then the question is, what will happen to your boat? And vorticity is defined by the rotation of your boat in this middle of this movement. I will be more precise now. Here's a picture. You see here a rigid rotation. You have water rotating around a circle. And your little boat is this red circle. And you look at the velocity in your boat. What you see is this. Of course, the points which are closer to the center of rotation have a smaller velocity, and the points which are further from the center of rotation have a higher velocity. So if you look at the velocity not with respect to the plane, but with respect to your boat, what you see is this. From your point of view, in your boat, you see that the velocity is rotating around you. So there is vorticity. The vorticity is the rotation of your boat, which is immersed in the fluid which is moving. So here's another example. This is a motion of water. So the water is, each element of water is going straight, but at not a constant velocity. So if you look at the velocity, you have the same phenomenon. The velocity in your boat is not constant. So seen from your point of view, you have the feeling that you rotate. There is vorticity. And the last example where there is no vorticity is where you have water rotating around a point, but with a velocity which is not constant. You see closer to the midpoint, velocity is bigger. So your small rowboat, red rowboat, you can see that the velocity around your rowboat is pushing in all directions so that globally you do not rotate. There is no vorticity. So probably I was not clear enough, so I will give you clear explanations in the following way. We should not believe that public lectures and diffusion of mathematics is a new topic. I will show you for 2 minutes a vintage film explaining what vorticity is, 1961. So listen to that.
The vorticity omega is defined as the curl of the velocity vector. Each fluid particle has a certain vector vorticity. The whole fluid space may be thought of as being threaded by vortex lines, which are everywhere tangent to the local vorticity vector. These vortex lines represent the local axis of spin of the fluid particle at each point. In 2 dimensions, the vorticity is the sum of the angular velocities omega A and omega B of any pair of mutually perpendicular fluid lines, AA and BB, passing through the point in question. This gadget is a vorticity meter, which floats in water with its axis vertical. The 2 vanes at the bottom are driven by the angular velocities of 2 mutually perpendicular fluid lines. So the arrow at the top turns at a rate equal to the average of these 2. That is, with half the vertical component of vorticity of the lump of water in which the vanes are immersed. This tank has been on the turntable for a long time, and viscosity has forced the water into a rigid body rotation. The vorticity float rotates almost exactly with the speed of the crossed white lines on the bottom of the tank. This is the plan view of a spiral vortex tank. Water passes from the reservoir through a flow straightener and into the tank through a tangential entry. It spirals round and round in a very tight vortex and finally leaves vertically through a drain in the center. What will the vorticity meter do? It doesn't rotate. It moves in pure translation, like the needle in a compass box mounted at the rim of a rotating turntable.
Okay, so now that you know what vorticity is, more or less, I'll show you a theorem. This is a theorem of a German mathematician, philosopher, scientist, engineer, everything, 57. The theorem is that in a perfect fluid, the vorticity is somehow constant. It is transported by the flow. So this means that if at some moment the flow is spinning somewhere, if you wait for some minutes or 1 hour or something, the vorticity is just transported by the flow. If the flow was spinning, it will be spinning forever. This is a theorem which fascinated Tate and Kelvin. And this fascination was the beginning of the theory I want to mention today. So, for example, Kelvin wrote, and you will understand again the religion point of view. Kelvin wrote, to generate or to destroy a vortex in a perfect fluid can only be the act of a creative power. So this means that if you have vorticity somewhere, it has to come from God. So I will not prove the theorem, but let me show you some beautiful pictures. This is a wonderful book that, well, I love. The proof is based on a very simple intuitive idea that in a perfect fluid, the forces that are acting on the object are pressures. And the pressure is perpendicular to a ball. So if you take a ball in the fluid, it is subject to forces which are perpendicular to the ball. There might be big or small, or we don't know, but the fact that the force is perpendicular to the boundary of the object clearly makes impossible to create rotation. It can push the ball, it can translate the ball, but it cannot spin it. That's the key of the proof of the theorem of Helmholtz. If something is not spinning, it will never spin. If something was spinning, it will spin forever. So Tate began translating this paper, and Tate was also a physicist. He wanted to see it by his eyes. So he decided to create machines to check that. And he invented this smoke ring cannon. So a smoke ring cannon is a box containing smoke, and you push a little bit on the bottom, and you have a ring of smoke which is going out of the box, and this is a smoke ring. And it's a stable object. And when Tate showed that to his friend Kelvin, Kelvin immediately understood that this should be the explanation for atoms. So we are in 1869. Atomic theory does not exist. We knew nothing about atoms. Some people didn't believe atoms could exist. And what Kelvin said is that an atom should be nothing more than a vortex in ether. So the theory of Kelvin, the atom vortex theory, is that our space is filled with some fluid that you don't know exactly what it is, some kind of ether, and this fluid is moving and is carrying vorticity. Vorticity being created by God. And these rings of fluids would be what an atom is. So we have to understand that at this time, nothing was known about atoms, and what are the fundamental properties of atoms? Well, they should be stable, and these things are stable. They just travel in space. They should be impossible to break into pieces. And among the first experiments that Tate and Kelvin did, They had a knife, and they tried to slice a smoke ring. And I don't know if you ever tried to do that. You cannot do that. You know, the knife does not cut the vortex. They are stable. And moreover, atoms were expected to send radiations. And you could expect that these smoke rings could vibrate and transmit to this medium some vibrations that could be what you see when you're an astronomer, when you look at light. So this was a very intelligent and clever theory for matter. An atom would be nothing more than a ring in space, rotating, spinning. So people wanted to check all of this. And another important property of atoms is that they should interact. You should explain chemistry. What's happening when an atom meets another atom? And then they made experiments, and I show you this from Japanese television.
続いて20メートル。
ろうそく着火。空気砲発射まで5秒前。
この曲もちょっと興奮するんだ。
2、1、発射。
ああ、いかないか。ちょっと小さく弱くなって。でも中心はすごい回ってるんですね。おお。これワクワクするね。はあ、面白いこれ。どうだ。消えた。
消えた。
すごい。
So speaking about interactions of atoms, we could think, how do smoke rings interact? And they began making experiments, and his beautiful picture. This I will skip that. This I wanted to put formulas. I want, you know. This is a beautiful phenomenon. You have two smoke rings. One is small, the other one is big. The small one is going fast. The big one is going slowly. The small one goes through the big one, and at the moment of proximity, they interact. The small begins to be bigger, the big begins to be smaller, and you have this movement of leapfrog. So this is a picture. This is a film. This is a computer simulation. Two interacting smoke rings. And this is amazing, yeah? So again, this is something that was very important for Kelvin. Atoms should be stable, it should be impossible to break them, and they should be able to interact and produce some kind of a nice interaction. This theory didn't work. It started in 1869. Kelvin wrote many papers. Tate wrote many papers. There was a lot of criticisms, and the theory was wrong. And they wanted to fix it, and they changed the theory of vortex atoms by another theory, which is called the vortex sponge, even more complicated and also wrong. And in 1905, Kelvin finally agreed that the theory was wrong. He wrote, "After many years of failure to prove that the motion of an ordinary circular ring is stable, I came to the conclusion that it is essentially unstable, and that its fate must be to become dissipated. So this was the end of the theory. So I just noticed I wanted to show you that. Look at that. The stability of atoms. Amazing.
Of 1,000 eyes, I saw the melting colors in the sky. I felt the heartbeat of the inner core. I saw a revolution dancing on the floor.
It goes forever and ever. Okay, so the theory was wrong. So now, okay, it was wrong. Now I want to describe for you what was the output of this wrong theory. And I want to show you one of the most interesting consequences is a book written by Tate. You can see on the top the trefoil knot. The title is The Unseen Universe. It's a crazy book. It's, but it's an amazing book. And what I think is that it is kind of a typical of the Victorian way of thinking science and philosophy and religion. It's very interesting. So the idea of this book is that God created vortices, but these vortices are dissipated, but there is another world of dimension 4, which is above us, in which this dissipation is transmitted. And there is another fluid in this 4-dimensional space in which there is also dissipation, but less. And there is a space of dimension 5 and 6 and 7. And this sequence of spaces is what God created. And you can see there, things which are not seen are eternal. It's really an attempt to connect science and religion, to connect mathematics, physics, and the life after death. This is, again, we are not used to that today. This is something we should not expect from a serious physicist. But this book was a great success. And indeed, it was such a success that he wrote another book which goes even beyond discussing vortices in high-dimensional spaces and try to connect that with our life, our death, our destiny, eternity, etc., etc. And I cannot resist from mentioning to you the sentence that one finds on the page 1. I will show it to you. It's a quotation from Kepler. And be prepared. This is a quotation from Kepler which connects with the fact that Kelvin was a creationist. He was convinced that space had been created by God as it is today. And here's what Kepler said. Yesterday, when weary with writing and my mind quite dusty with considering these atoms, I was called for supper. And the salad I had asked for was set before me. It seems then, said I aloud, that if pewter is it? Pewter? If pewter dishes leaves of lettuce, grains of salt, drops of water, vinegar and oil, and slices of eggs had been floating about in the air from all eternity, it might at last happen by chance that they would come a salad. Yes, says my wife, but not so nice and well dressed as this of mine is. So I like this because this is page 1 of this book. So this is the idea that the world as we know it cannot be the result of randomness. You need your wife. I chose two books published by respectable editors 2 years ago, which contain essentially the same things. So these ideas are not new, they continue to exist in the general public. This is something important. People are mixing science and philosophy and religion, and why not? Okay, let's go to Maxwell. Maxwell is probably the greatest physicist of the 19th century. He's not French. And Maxwell was a close friend of Tate and a close friend of Kelvin. And they exchanged many letters. But Maxwell was not satisfied with this connection between science and religion. He didn't like that. He wanted to make a distinction. And indeed, this book of his friend Tate on the unseen and the life after death, etc., he did not like it at all, especially because he knew he was dying, and indeed he died a few months later. So he wanted to make fun of his friend, and he wrote a poem to express the fact that the book of his friend was ridiculous. So here's the poem. It's a first for me. I was declaring a poem in public. I didn't do that since my primary school. And to do that in English is even more complicated, and even more using some words that maybe some of you don't even know because it's archaic English, I think. Here's what it has. This is the poem. My soul is an amphitheral knot upon a liquid vortex wrought by intellect in the unseen residing, while thou dost like a convict sit, with marlinspike untwisting it, only to find my knottiness abiding, since all the tools for my untying in four-dimensional space are lying. Where playful fancy intersperses, whole avenues of universes, where Klein and Clifford fill the void with one unbounded finite homaloid, whereby the infinite is hopelessly destroyed. And the poem is infinitely long. Well, most of the words were unknown to me. For example, I didn't know what marlinspike is. Does that belong to the standard English dictionary? You know? It's a tool, no? A tool for, you know? Okay, okay. What I didn't know was, this I knew it. I know what homaloid is. I'm pretty sure that not so many people in the audience know what homaloid is. I'm the only one. So homaloid is the space between two ellipsoids. Take an ellipsoid, a sub-ellipsoid, the shell between the two is called an homaloid in all algebraic geometry books. So that's one of the consequences of this wrong theory. Now, when Kelvin decided that it could be a good idea to associate atoms with vortices, Kelvin said to his friend Tate, why don't you make a list of all possible knots? For each knot would be associated a chemical element. So maybe this knot will be oxygen, and the trefoil knot would be, and this would be nitrogen, and maybe you can find a list of all possible knots, and then once you finish your list, we will look at trying to connect that with actual chemistry. And Tate did it. So he wrote papers. Here's one page of one of the papers. He wrote papers containing lists of knots. 2 pages and pages and pages. You know, it's not easy at all. You have to find a list of knots. You have to make sure that the knots that you are not the same. And you have to make sure that your list is complete. And Tate had no tool, had no mathematical tool to do that. And he was very clever, and he basically made no mistakes. Today we have efficient tools, and people could check the tables of Tate, and they are correct. So here's a modern table due to Rolfsen. This is basically the same. And indeed, Tate spent a long time trying to classify all possible knots. By the way, I want to mention that in 1869, Mendeleev had not published his table of elements, his periodic table of elements. So the idea of writing some kind of combinatorial description of all possible atoms is something very, very fundamental and very important to understand the list of atoms and to connect it with a mathematical topological structure was something really fantastic and very important. So that's a very useful consequence of the work of Tate. Tate worked hard, indeed. These are the knots. Tate made a conjecture. And this conjecture has been solved recently. So I wanted to mention this conjecture. For some reason that I don't quite understand, Tate was only interested by what we call alternating knots. You see, I took a knot at random, and you see that the strand is going up, down, up, down, up, down, up, down. So it's a knot which is such that the crossings are alternating, below, up, etc., etc., etc. And one of the questions of Tate was, if I draw on a sheet of paper, if I draw a knot with this kind of alternation between up and downs, is it possible to draw it in a different way with less crossings? Could it be possible that alternating knots represent knots in their lowest possible complexity, with the smallest number of crossings? So if you take this knot, for example, it has 10 crossings. Is it possible to change it and to put it on the plane in some different way with less than 10 crossings? Can you make simpler than that? Is it true or not that a knot which is alternating is in its simplest presentation? The answer is, of course, not. Here's an example where it is not the case. If you have a knot, like on the upper, the yellow and blue, you have a knot which is composed of 2 components. You have a complicated knot here, another complicated knot here, and you have this crossing. Clearly, if you have this situation, you can flip the blue to get the blue, and you have one less crossing. So the actual good question is, suppose you are not in this situation. That is, you have an alternating knot in the plane, and you assume that this does not happen. It's called a reduced alternating knot. Is it true or not that it is in the simplest possible configuration? This is the conjecture of Tate, that he worked hard on it, and which was finally proved in 87 by Kaufmann, Murazugi, and a non-French mathematician. whose name is impossible to pronounce. Thistlethwaite? Thistlethwaite? So, Thistlethwaite. So Tate would have been so satisfied to see that his conjecture was satisfied. Okay, now to finish, I want to discuss 3 examples of results which are new and which are connected with states and with knot theory and with fluids and with vortices. I've chosen them because they are somehow, you know, we have in this meeting we have four workshops. One is discussing fluids, one is discussing topology, one is discussing number theory, and the fourth is you are in charge. The fourth is discussing mathematics. Huh? Okay. So my goal was to give you examples of 3 results, one in each of these 3 categories that Tate would have liked. The first is somehow related to, not in a direct way, but is somehow related to me. About 9 years ago, I was thinking about these vortices and knots and dynamics and blah, blah. And I was led to understand the connection between knots, vortices, and prime numbers, and more precisely, ideals in quadratic fields. I was happy with that. And I did some pictures. I was happy with this. And it turned out that some people from number theory were interested by that. Peter Sarnak wrote a beautiful paper trying to understand better what I had done. And very recently, it's not even published, it's not even on the archive. There is a preprint going even further. And so, you know, my name is there. So I was so happy to see that mathematics is moving, is making progress, and you know, there is a connection between between knots, vorticity, cocycles, modular group, prime numbers, quadratic fields, etc., etc. I like it very much. But more important is that from the motion of fluids, there was very recently, a paper. I love it. Even though I cannot guarantee that I checked everything because it's a long paper full of PDEs, which is far from being my expertise. But in this paper, 2015, the authors prove that Kelvin was somehow right. They prove that there does exist fluids moving in space in such a way that the vorticity is making knots. And actually any knot. You give me one knot, there exists a motion of some fluid for which the vorticity is linked in exactly this situation. It's a beautiful paper. Well, it depends what you call beautiful because it's full of formulas. But the theorem is this. I'm not sure Tate would have understood it. But this is somehow the solution of a conjecture of Tate. And the final application, final development I want to show you now is due to physicists. Can you actually construct a smoke ring in the shape of a knot? Can you do it? Can you know, you have seen this guy doing with a complicated smoke ring with his mouth, but the mouth is not knotted. Can you blow a knotted vortex rings? This is a wonderful question. I've been asking that to myself for 30 years. And they did it. They did it, and this is a recent result by a group of physicists. I will show you that. It's something really interesting, I think. This is a paper by this physicist, Creation and Dynamics of Knotted Vortices. And I will show you the first sentences of this paper to show you that somehow physicists sometimes write better than mathematicians because you understand. Whereas tying a shoelace into knots is a relatively simple affair, tying a field, for example, a magnetic field, into a knot is a different story. The entire space filling field must be twisted everywhere to match the knot being tied at the core. So they do it. And not only they do it, but they produced a movie showing how they did it. So here's the first movie. As the first movie, there will be no knot. So you see what's happening? There is a circular object in the liquid, and all of a sudden, it goes down. So it produces a ring, in this case of water. This is the same ring that we have seen with the dolphins. No news. Now the idea of these physicists is, what if we use a ring like that? So they use the 3D printer to print this kind of object, which is like an airplane wing, except that the wing is knotted. So you put this object, it's big like that, you put that in a liquid, and you will throw it quickly in the water. It will produce something which hopefully will be linked and will hopefully produce a knot. And indeed, this is what happens, and I show you the movie. You have to look carefully because the motion is quick at the beginning. Up. Look. So they did produce a trefoil knot in water using a knotted aeroplane. Let's have a second look. Hop. Very quick. And I think that the film is even the velocity of the film is even reduced.
Was the airplane wing and trefoil knot too?
What? Yes, it was. Yes, the final shape of the vortex ring is the same as it used to be for the object that you put in the water. And you can do that with different. If you want to do that at home, you buy a 3D printer and you do it, and you can do it. But you see at the end of the film, you see that the dissipation, the viscosity, somehow killed the vortex after a few minutes. And this is what Kelvin explained, and this is why his theory was not stable. But you know, you have dissipation here, but who knows? Maybe there is no dissipation in dimension 4 and 5 and 6. I don't know. Okay, I'm finished. I just want to thank you and to show you this beautiful picture of Leonardo da Vinci, 1517. Look at the precision, the way he was looking at nature. This is really wonderful vortices. He had understood the theorem of Helmholtz, maybe. Thank you very much.